Hello, welcome back to the Philip J. Currie Dinosaur Museum Virtual Speaker Series, where we have paleontology guests call in for a presentation on science, fossils, and dinosaurs, and where the public will be able to ask questions live on YouTube. First off, we want to acknowledge that we are on the homeland of the many diverse First Nations and Métis people whose ancestors have walked this land since time immemorial. We are grateful to work, live, and learn on the traditional territory of Treaty 8. Today, Mark Powers will be presenting the evolution of EUDROMAEOSAURIA. Biogeography led to strong divergent trends. Mark Powers is a Canadian PhD student studying vertebrate paleontology at the University of Alberta. He completed his master's degree at the University of Alberta under the supervision of Dr. Philip Currie. During Mark's master's studies, he researched Dromaeosaurid, that is, raptor dinosaurs, evolution and ecology. His thesis focuses on the trends in snout shapes through evolution and included the description of a new species of Velociraptor. His PhD studies are focused on the evolution of snake lizards leading up to modern diversity, including the advent of macrostomy. The ability to consume massive prey evolved. For the viewers at home, you can leave your questions in the comment section and I'll read them to our speaker at the end of the talk. Thank you, Mark, for joining us today. And with that, I will let you take it away.
Thank you very much, Kala. I'm not sure, I was just gonna ask one quick question. Should I have my video on or off for this?
Go ahead and turn your video on.
Okay. Okay, so hello everybody out there in the YouTubes. Thanks for joining in on the talk and sitting in. Today I'm going to be talking about my master's thesis, as Kala had mentioned. And I got to study the evolution of dromaeosaurids and sort of their biogeography and how that impacted their evolution and disparate morphology. So with that, thank you very much for the introduction, and thank you to the Philip J. Currie Museum for hosting and inviting me. This is my first live YouTube talk ever, so hopefully I don't stumble too much and make a mess of it, but with that, we can carry on. Oh, will it work? Uh-oh. Sorry, everybody. Oh, there we go. Yeah, so to start off, I would just like to say that I live on and I am presenting from Treaty 6 territory, the traditional gathering place for diverse Indigenous peoples, including the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwa, Saulteaux, and Anishinaabe, Inuit, and many others whose languages and cultures continue to impact our community. Yes, and moving on with that, I think that we can't help but address the recent events of finding the unmarked graves of numerous children from the residential school system that was in place for over 100 years. This represents a dark and horrific time in Canadian history, and many children were taken to these institutions and were attempted to be assimilated into white culture through very atrocious means. And with that, I think that we deserve, or we owe them, a minute of silence here just to honor and respect those that lost their lives in these institutions. So with that, I will take a minute, and I hope that you do too, to reflect on how we are involved in all this. Thank you all for joining me for that minute. And if you want to learn more about Indigenous history here in Canada, feel free to go to the coursera.org and Indigenous Canada. And there's a free online course that is a very good starting place to learn more about our history and our impact with Indigenous peoples. As a white man myself, it's tough to talk about these things and to address these issues and figure out my role in all this, but I look forward to moving on and learning more to have a more impactful, more impact moving forward with these issues. And with that, I thank you for your time, and I'll move on to the talk for today. So going into it, I'll talk a little bit about myself. So I'm an avid paleontology lover. A lot of the photos of me are me in the field. Oftentimes I'm pretending to fire off megaton blasts like my hero Goku. My other passions include looking for modern day dinosaurs, so going out birding and looking for those feathery friends. And I grew up in a small town called Eckville in Alberta, and it's famous for all the wrong reasons. So those of you might know why, and those that don't, feel free to ask me about it. It's more so silly. I don't have association with it, but anyhow. And in general, the last year and a half has been really difficult for us all. So I couldn't have made it through myself without the help of my family, my son Adam, my partner Stephanie, and of course, my furry friends Goku and Thanos. Yes, I even named one of my cats Goku, and he's not an alcoholic, I swear. And then, so why did I get into paleontology? Well, this question, a lot of people have a very similar answer, and mine's pretty close. And generally, it's that paleontology is always fascinating, and dinosaurs are always capturing our imagination and making us want to learn more. And it very much did the same for me, but not right off the bat. Initially, Jurassic Park came out when I was 2, and my mom took me to see it in the theaters. And I was so scared, I was vibrated with fear, and she had to remove me from the theater, and I couldn't finish the movie then. But when it came out on VHS, I had to have it. They don't know why. And I would watch it over and over and over again. And every time the T-Rex would come on, I would run out of the room and hide and peek around the door frame till eventually I could sit through the whole movie. And then it eventually became my favorite of all time. I think even to this day, the first Jurassic Park still holds that title. But that really got me into science more generally. And as I went through school, I kind of jumped back and forth between biology, physics, chemistry. All of them were so interesting to me. And when I was deciding what I was going to do going back into university, I was actually stuck between astrophysics and paleontology, the two most captivating things I think any kid or person more generally could ever possibly want to do. But as I was mulling it over, I was holding the ultimate book of dinosaurs and drawing scale-sized dinosaur pictures in my little notepad, and I was writing down facts about them. And I kind of just realized, I think my heart is in this more than anything. So from that point, I decided, and I started at Red Deer College for 2 years before going on to the University of Alberta, which Kala had mentioned about my history and where I'm at now. So with that, I will talk about my master's thesis largely, and that's where I described the evolutionary trends in dromaeosaurs. So what is a dromaeosaur? So when you think of dromaeosaur, you typically think of the raptor dinosaurs. And Jurassic Park has made this remarkably famous, and the new Jurassic Worlds have even made superheroes out of them, in a sense, when you think about blue. But when you think about it more taxonomically or a paleontology sort of standpoint, it really means a member of the family Dromaeosauridae. And this family name means the swift lizard family. So this idea of them being swift lizards is a very old one. Excuse me, sorry. And it's really led to some fantastical and romanticized ideas, such as the scene in Jurassic World where Chris Pratt is driving his motorcycle and all 4 raptors are keeping up with him for a really prolonged period of time. In reality, they weren't the speediest of animals. They were small and probably agile, but not necessarily sprinters or long distance runners. If real dromaeosaurs had been in that running scene with Chris Pratt, they probably would have keeled over after the first few seconds and died of an exploding heart and torn muscle. It would have been bad for them, very ugly. So the history goes all the way back to 1922 with the discovery of Dromaeosaurus albertensis. So like the family, this means the swift lizard from Alberta. And 2 years later, Velociraptor mongoliensis was also described. So these two were described fairly close to each other, and no formal family was made for them at this time. It was just recognized that they were something small, gracile, and different from these large theropods like tyrannosaurs or allosaurs. And then there was an almost 50-year hiatus of finding anything like them until the description of Deinonychus. The description of Deinonychus changed everything in terms of how we even look at dinosaurs. But what it really did is it solidified that there was a family of dromaeosaurids, which all shared anatomical features with each other, more so than the other theropods. And it really changed the idea of lumbering beasts to agile and active animals that were probably more comparable to the modern mammals and birds of today. These discoveries picked up in intensity over the years, with the turn of the millennium having additional discoveries at a much faster rate. So Ecolobatar is a giant dromaeosaur from Asia. found in 1999, and Bambiraptor is a very bird-like dromaeosaur from here in North America. The most complete skeleton of Bambiraptor is actually a juvenile, so it was thought for a long time that Bambiraptor might actually be just the juvenile form of Sornitholestes, which is not the case, but I'll kind of glaze over that, obviously. So EUDROMAEOSAURIA, as the title implies, is not just dromaeosaurids, or not the whole group of dromaeosaurids. It actually just represents the derived dromaeosaurids, and these EUDROMAEOSAURIANs are really what you probably think of when you think of a raptor dinosaur. These are the terrestrial predator raptors. They're larger than most of their other family, and they have predatory adaptations that are very obvious. And within EUDROMAEOSAURIA, there's actually 3 subfamilies. The Sornitholestinae from North America, at the late Cretaceous of North America, Velociraptorinae of the late Cretaceous of Asia, and then Dromaeosaurinae, which stretches from the early Cretaceous to the late Cretaceous, with members from both Asia and North America. So the raptors, or true dromaeosaurids, as mentioned, really are the ones that you probably think of. And I've talked about those predatory adaptations, and you can see their teeth here. But one of the most iconic things is their claws. A lot of people really gravitate towards this feature. And if we use the Jurassic Park example, we think back to that scene with the raptors tapping their claw real condescendingly as they're looking for the kids. So we'll look at some real examples or some actual photos. And when we see the raptorial claw on a specimen, we see that it's usually curved or curled upwards as opposed to the other digits which curl downwards. So this has led to a lot of evidence to suggest that they actually kept these claws up, and the footprint evidence supports this as well. So they actually kept these claws off the ground and didn't use them for walking. So they had to serve some other purpose. And the thought is that they were either a slashing or grabbing tool. Further details about the claw have come up with the Sornitholestes specimen at the University of Alberta. And this one actually preserves some bits of keratin still. So it actually shows that the claw was much longer in life. And although it's just a thin wisp off the end, it probably would have made the claw a little thicker too, in terms of a keratinous sheath around the entire element. The hand claws were quite different. In cross-section, they were more rounded. They didn't have an angled or ridged leading edge like the raptorial claw, and they were generally more recurved, so they were more like a hook. And then their snouts with the serrated teeth. So much like tyrannosaurs or allosaurs, they had relatively few but large and serrated teeth in their jaws. All these things together show a clear indication that dromaeosaurs, and particularly EUDROMAEOSAURIANs, were active and efficient predators. So this trend between Asia and North America and the representatives of dromaeosaurids from either or really started back in 1999 when Barsbold and Osmolska did a detailed description of Velociraptor's skull. And what they really honed in on were the elongate features of the snout and other cranial bones that they compared to North American specimens. This really sort of jump-started this idea of this distinct geographic separation, and it was sort of the incitement to a number of morphological characters to actually try to understand their evolutionary relationships. What this didn't really capture, however, was what might be the reason that they had this disparate morphology. What was causing them to have these unique morphologies from one another? So that's when we look into something called form and function. So morphology changes throughout time as an adaptation or over generations to adapt to different environments and different coeval species and things that are interacting with the organism. So the Darwin's finches on the left is a really, popular example. And this example really kind of just showcases how beaks can change quite drastically to utilize different food sources to reduce competition between coexisting species. And over the seasons, these beak shapes would actually change and the predominance of one species would fluctuate. So they really follow these ecological trends quite readily. If we look at birds more broadly, we definitely see that the beak certainly serves a number of functions, from the flat bill of a duck for filter feeding out things that it grabs in the water, the long bill of sandpipers and other things to spear or grab specific little small prey, and then the raptorial beaks, which are recurved at the tip and typically much deeper. And this is used to tear and render flesh, or rend flesh, not render, I can't create flesh. And so this is something that we would call convergent amongst the two raptorial families, actually 3. I don't have an owl picture here, but owls, falcons, and hawks. Those 3 all have converged on a very similar beak morphology. So convergence or homoplasy is when form and function kind of meet you know, they follow a similar pathway to solve a similar problem. And this is most commonly exemplified in wings. We all know about pterosaur, bat, and bird wings. They all flew, but we also recognize that they're not close relatives. And the reason we can tell that is when we look at the wings themselves, they're composed of not different elements, but a different arrangement and morphology of the elements of the wing. This is much like flippers. When animals return to the water, oftentimes their appendages become adapted to maneuver through the water and provide balance in the form of flippers. And when you look at them as a flipper, they might seem the same. But when you look at the bones that comprise those flippers, they're quite different. And that's how we tell families like mosasaurs, ichthyosaurs, and plesiosaurs all apart from each other, despite them all having flippers. So this is where convergence is versus homology. And homology would be the shape and structure of each bone within that. So if we look at a modern raptor example of form and function for claws, coming back to our predatory arsenal, there's been studies that have looked at the shapes of the claws as well as observing behaviors to see if the shape, you know, clusters into groups based on behavior. And sure enough, when you compare the claws of the foot of the accipiters or the hawks and eagles in red, we see that they cluster together because they have a very specific style of grabbing hold of their prey and puncturing it with their claws as they lacerate and tear through it with their beak and other foot. Falcons do a very similar thing, falcons being in blue, but they also grab birds out of the air. So they have much longer toes and their claw proportions are a little bit different than hawks and eagles. When we look at the owls in green, we actually see that they have their own little cluster as well. And this actually is indicative of the fact that they grab hold of their entire prey, typically feeding on small mammals, and then using the strength of their foot, they actually crush and break the bones of their prey to, you know, kill it or immobilize it. And then the osprey is the orange arrow here. And the osprey has probably the most iconic looking claws out of all these, and they're very recurved and they're all quite large. And this is because it grabs fish. It's a fish specialist and it needs to make sure that it hooks and catches its fish and that they don't get away from it. So if we make the same sort of thought experiment with the claws, just to look at the range of morphology as well as what are some possible functions, with the whole caveat that we don't know for sure because we can't observe them in their actual environment. So we have to look at the morphology and see what our modern can inform us about it. So this is the foot of Deinonychus, which shows its raptorial claw raised, and it has a dotted outline showing where the keratinous sheath would be, or hypothesized to be by Ostrom at the time. And to test the idea that these might be a kicking or slashing tool, Manning et al. Decided to build a robotic Deinonychus leg and use a Deinonychus claw on a sort of mesh sheet or a skin-like sheet to just see what it could do. And they found that it didn't do very well at cutting, but instead was good at just gripping or piercing and just holding. Now, the one major issue with this is that they used just the bone underneath, and it didn't actually have the keratinous cover. So the sharpness of it might have been greatly reduced because of this. When we compare this to the Velociraptor or fighting dinosaur specimen, we can see that the claws are actually being used in a different way. They're being sort of set straight out, and they seem to be positioned close to the throat of the Protoceratops. However, this also has a caveat in the sense that the claws, as we know in preservation, typically retract upwards, whereas the toes, the other toes without the raptorial claw, retract downwards. So this could be a case of just drying tendons, locking it in that position. However, it is still possible that it might have been slashing into its prey. Going further, Fowler et al. Looked at Deinonychus once again and actually did compare it to the accipiter morphology in the sense that the raptorial claw is quite large and the range of motion really gave them the ability to grab hold and hold down their prey. So it's thought that maybe Deinonychus was doing the same thing. However, not all claws are created equal. When we compare Saurithalestes' raptorial claw to Deinonychus, it's much less recurved and actually more similar to Velociraptor. Given the less curvature to this claw, it probably would have been more suited for a slashing or at least one deep or wide scoping range of motion that might have cut quite a nasty wound into its prey, rather than Deinonychus, which may have been a bit better for just holding and pinning. The hand claws, as mentioned before, are more recurved, similar to Deinonychus's raptorial claw, and you can see them in Velociraptor just kind of holding on to the face of the Protoceratops. So these claws didn't have a lot of power as the hands were quite delicate, but due to their shape, they would have made great meat hooks and provided a good anchoring on prey if they needed to bite or lacerate it with their claws. However, as we move to the late Cretaceous, most dromaeosaurs seem to have a very similar morphology, which was more of this possible slashing morphology in that they had a less recurved raptorial claw and it was quite long. All of them do have a sharp leading edge, similar to the Deinonychus and other dromaeosaurs, so it does suggest that the keratinous sheath might have also had a sharp leading edge. So now let's talk about the snout side of this. The snout side of it is much more studied and broadly sort of ground truth is the word I was looking for, in the modern. So we can see a lot of behaviors in modern animals, and we can do morphometrics or look at their morphology and compare their behaviors to that morphology. So using this, we then compare it to the fossil record. So one example being grazing versus browsing in ungulates and comparing it to hadrosaurs and sauropods. And it was found that there are similar trends in snout proportions between hadrosaurs and also sauropods that reflect what ungulates do today, with broad, wide snouts being better for grabbing, for the grazing, and then the browsing, more selective feeding, having a more narrow snout. This has also been done in the modern for things like bats, where they did a very wide set morphometric analysis. So this took many measurements of the entire skull, particularly the snout region, and they were able to positively identify groupings based on diet, up to 7 different diets in bats. So there's clearly this correlation between cranial shape and diet, at least in modern animals and probably in the fossil record. One that's more relevant to this comparison or this study is the skull shape of canids and the relationship to their prey specialization. And the reason it's a good comparison to, say, dromaeosaurs is not because they're closely related in terms of, mammals and dinosaurs being closely related. That's not true. But what they are closely related to is in their ecological niche, in the sense that they both fill the small predator, sometimes to maybe up to medium-sized predator, in their respective ecosystems. So it stands to reason they might experience similar morphological pressures, especially for acquiring food. So the one I will bring up a lot throughout this talk is the Slater et al. 2009 study, where they looked at the preference of diet, the snout shape, and also created models to test the forces applied to those skulls pertaining to the prey specialization. So this is a good opportunity to look at homoplasia and homology. So where do things converge in trying to follow a function, and what tells us about the ancestry of a group? What is something that's shared between all of the living members and their ancestors, or their most recent ancestors? So Slater et al., as mentioned, looked at the snout shape of 3 different types of canids. There were the long-snouted, the intermediate, and then the short, broad-snouted individuals. And when looking at these types of individuals and their diet in the wild, they found that there was distinct groupings between small prey specialists with very long snouts, generalists with intermediate morphology, and then large prey specialists with the short, wide snouts. They also looked at the models of the skulls and compared them under the forces of biting, as well as the forces that a prey item might imbue onto the skull when they're resisting. So basically the extrinsic forces on the skull as it's trying to hold its prey. And what they found was that the short, wide-snouted individuals were almost overly well built to handle those types of forces, meaning that they didn't have a lot of weakness when they were trying to hold their prey. Whereas the long-snouted ones tended to have rapid biting, but not actually have that much power. They use the schematic between their different groups: triangle, large prey; generalist, square; circle, small prey. And they plotted out on their phylogeny that they constructed using a mix of morphological as well as molecular data. And what they found is that snout shape really could jump all over the place. There was a few examples of the total opposite snout shapes being sister related or being most closely related, such as in Canis lupus and Canis latrans, which are the wolf and coyote respectively. As you know, or as you might know, the wolf or gray wolf is a large prey specialist, usually hunting things like elk, deer, bison, with a pack usually. It has a number of individuals that help it out to take down big prey. A coyote, on the other hand, tends to favor small prey, but be opportunistic in anything that kind of comes its way. So you'll more likely see it feeding on rodents and rabbits and things of those sorts. Now, you can have a case of homology, in which case a whole family or a whole group tends to have one single morphology, and that's probably because they've evolved always staying in that niche. So the example here is the Vulpes genus. Most of them, except for Vulpes Chama and Phenicus zerda. I'm not great with these Latin names. But anyways, this whole group has the small prey specialization, as well as that morphology of an elongate snout. So it shows that it can be fixed. And that is where we have a case that we could say that is homologous within the group, and it has been in their ancestry for a while, having that condition. So this was a virtual abstract done by Nuria Melissa Morales Garcia, and it's just a way to show that study in a very quick way. So I just rambled for a whole big period of time, a lot of time there, and this shows it much more efficiently, saying that, you know, longer jaws leads to weaker bite force, but also has the benefit of closing your jaws faster. So you're better at grabbing small, quick moving prey. Whereas if you move to the other side of the spectrum, you have an increased bite force, but your jaws become shorter and your jaws don't close as fast. So carrying this on and moving the comparison into the dromaeosaurid realm, what we can see is that even in these 3 select dromaeosaurids on the side, we see 3 different snouts. And I do apologize for the googly eyes. I tried it to see what it would look like, and it was horrifying, but I chose to keep it because why not? We live with our mistakes, I guess. And anyways, so they too have different snout morphologies that are fairly obvious to see at a glance. But whether or not these are related to ecology needs more work and evidence to investigate. But where we can find homology in this is the bones that actually make up the snout. And despite them not being closely related, dromaeosaurids and canids do share most of the same bones in the snout. So they have a premaxilla at the front, a nasal on top, a maxilla on the side, and then a dentary to make up the lower jaw. They have the same orbits at the front, which are the nares or nose hole. But what the dromaeosaurids do have that is distinct is the antorbital fenestra. And this is a homologous feature, as we were talking about, that is shared amongst archosaurs. So crocodilians and birds today are our modern archosaurs, and most dinosaurs had this fenestra unless it was secondarily lost. So to look at the uses of the snout for dromaeosaurians, EUDROMAEOSAURIANs, we have to look at certain lines of evidence. And in a study in 2018 by Thesis et al., they looked at microwear patterns, which showed a 2-phase action in terms of biting and trying to feed for theropod dinosaurs, which included dromaeosaurs as well as tyrannosaurs. And this 2-phase sort of assault was the bite and rip strategy. So this strategy is actually used by modern day Komodo dragons, and it's because their teeth are very similar, more likely, and that they aren't necessarily always trying to overpower their prey, but instead to leave rending bites that wound their prey. Another way to look at the morphology and how it functions is to take morphological models and then apply forces that are supposed to be simulations. There we go. Man, it's been a heat wave and my brain has turned to pudding. So the simulations are essentially to show what its behaviors might be, so such as biting and tearing. And then it shows how that morphology responds to those forces. And you can see variations between different species. And if one is more resistant to certain forces than the other, then it might have behaved slightly differently in terms of its feeding. So that's what I mentioned Slater had done with the mammal skulls. It's not been done with all the sort of skulls of theropods, but it's building up in its data set. And just as a reminder, small prey example, the fox and the wolf here. So one thing to look for as an initial test is if there's some kind of trend in dromaeosaurids that are showing the same distribution in snout dimensions. What could be done after a trend like that is found is looking at the morphology and how it dissipates forces, as I mentioned before, like in Rayfield 2001, where they looked at an Allosaurus skull. The other way is to look at them like a mechanical system. And so to do this, you look at the musculature of the skull, as well as the length of the jaw, the curvature of the jaw, the tooth positions, and you can kind of get a sense of how efficient is that jaw. And that's what Sakamoto 2010 did. And what they found is that dromaeosaurs tended to be in the weak, fast biting category. They didn't seem to have these highly efficient jaws like tyrannosaurs did. But that's with the exception of one dromaeosaur, Dromaeosaurus albertensis. This species seems to have a very high efficient bite, so a strong bite force. And the specimen, the parts that are preserved, show that it is a very robust skull. Now, it's suspected that Dromaeosaurus probably was more of not a large prey specialist, but in the sense a biter, something that would very much rely on its bite. And we don't actually have the top of the snout, so we can't get an exact shape for it, but we do have the general robustness to go on for this taxon in particular. So to look at our trends, we have to sort of look at the diversity of EUDROMAEOSAURIA. And unfortunately, it's not the most sexy looking group of dromaeosaurs. They're not all complete skeletons. There are a few, and there's some that have many representatives. But generally speaking, they're known from little bits of material. And that's why the diversity of EUDROMAEOSAURIA often looks like this image on the right. This is a picture of a bunch of maxillae, so the upper jawbone of EUDROMAEOSAURIANs. And the reason for this is that sometimes all we find are a few elements to describe a species off of. And the maxilla is considered very diagnostic. So these are 3 examples of species that are predominantly described just based on the maxilla. And that's a Chiroraptor to the left, a Troceraptor in the top middle, and then Velociraptor osmolske in the bottom middle. And the reason that the maxilla is given this much credit is because it's very complex. You'll look at this element and maybe think either it's not complex or you'll see the complexity right away. But I will show you some of the complexity it actually has, such as 3 processes which articulate with different bones of the skull. It has teeth and it has palate processes. It also has depressions and fenestrae or holes on the side of the maxilla for the sinus system that archosaurs have. And these are the 2 fenestrae, the promaxillary and the maxillary being the larger one to the right. And these fenestrae actually feed into the medial or inside of the maxilla, where there are 2 distinct chambers in most theropods and in some EUDROMAEOSAURIANs. And these 2 recesses are defined by 2 struts of bone that keep them sort of separate. This whole sinus system sits on top of the palatal shelf. And if you want to think of the palatal shelf of what it is, if you put your tongue up to the top of your mouth, that would be the palatal shelf. There's not the exact same in archosaurs, obviously, but that's the general idea. So the phylogenetic importance of the maxilla becomes very apparent when you look at recent data analyses looking at EUDROMAEOSAURIAN evolution. And out of 180 characters, 30 characters could be considered maxillary characters, which is almost 1/5 of the entire data set. So very important bone in identifying what species belongs where. Some of the characters that have been described, just quickly highlighting the 3 maxilla taxa that I mentioned before, as well as Deinonychus. Deinonychus is a sort of wild card taxon that sort of jumps around in its phylogenetic placement. But now I'll move on to the characters that have been used, some of which referring to that anterior or front plate on the maxilla and its proportions with the maxilla. So in Velociraptorians and Sorntelestines, it's considered long, greater than 25% the maxilla length. And in the dimensions of that anterior plate on its own, its length to height ratio, it's considered elongate only in Velociraptorinae and stout or short in the other ones. So because of this characterization and these characters sort of contributing to this idea of homology, a Chiroraptor was first described and recovered as a Velociraptorian. And this was largely due to that really long anterior plate of the maxilla. So I'm going to jump back to that comparison of Asian and North American. We have this idea that Velociraptorians and Velociraptor and all its close relatives must be closely related to things that have elongate features. But we can't know that until we rule out the functional aspect or that there's some trend in just dimensions of the maxilla. So when we go back to the actual description of a Chiroraptor, it's a bit of a conundrum. It's what do you do with something like this? When you look at it, it sure looks Velociraptorian from a glance. And so this led to some hypothesis that there may have been a dispersal of Velociraptorians into North America during the late Cretaceous, and that this elongate anterior ramus would equate to an elongate maxilla, even though it's missing part of the posterior portions. And then kind of stretching that on a little bit further to a generalized, if the maxilla is elongate, then the snout should be elongate, which makes some intuitive sense. It does make up most of the snout in the inside view. When we look at non-EUDROMAEOSAURIAN dromaeosaurs, however, we do see that the bones that make up the snout are quite different between different subfamilies and different groups, such as the Microraptorine above and the Hulscaraptorine below. So we can't really make generalizations of the snout across all dromaeosaurids, but perhaps if we stick just to EUDROMAEOSAURIANs, we might have more luck in making generalizations. So first we have to test, can the maxilla be a proxy for the snout shape? Can we just infer snout shape from the maxilla? And to do so, I took the dimensions of the premaxilla and the maxilla, so its length to height ratios, and I compared them along a linear regression to see if they had a good fit or if they were quite variable. And I was fortunate to find that they actually do have a pretty good fit with a little bit of variation, but nothing that really screams quite divergent from one another. So this does in fact mean that we can look at the maxilla, take its dimensions, and infer, generally speaking, the snout shape of that species or individual. So using the maxilla as a proxy now, we can look at a lot more dromaeosaurs. We can add more to this database and get more useful information from it. So now I'm going to walk through the way that I kind of went to look for a pattern of dimensions, as well as sort of getting a good hypothesis of relationship, and then inferring any possible functional aspect. So the first thing is to construct a hypothesis of homologous relationships, make a tree. It's the basic one. Everyone likes to look at cladograms and see how things are related. And just as an example, it's made up of a number of characters which atomize the morphology into a code, you might say. And then this is compared amongst all the individuals, and you get their closest relationship based on the most similarity, more or less. After we have that tree of their phylogenetic relationships, we can then look at the trends in snout dimensions more broadly and look at them just in how they sort of plot and fit together in a gross morphological kind of way. And then lastly, we can take those dimensions and we can plot it over our phylogeny, much like Slater did in 2009 with canids, and we can see what were the trends in evolution for snout shape throughout the Cretaceous for dromaeosaurs or EUDROMAEOSAURIANs. So to start by doing this, I was fortunate enough to get a lot of CT scans, which are great for examining anatomy that either is obscured by rock, or if it's crushed, you can retro-deform it. So this is where I started really looking and comparing morphological characteristics to see what were good comparisons to make. And this starts by reanalyzing specimens that haven't been reanalyzed in a long time. Deinonychus is a specimen that was described in 1969. And it hasn't actually been redescribed or looked at in great detail again until now for this element at least. But based on its old description and how it appears, it's inferred that this whole element there and all that's outlined in blue is actually the maxilla. And this has led to reconstructions, this one by Scott Hartman, showing that the maxilla was quite elongate, and it does seem to fit into that Velociraptorian niche of being elongate and very, long snouted in general. However, when we look at the CT slices through the specimen, we can actually see that Deinonychus has a really well-developed sinus system. And because of this, we can actually track the boundaries between the bones of the snout. And it is found when looking at multiple sections in different planes that the premaxilla and nasals are still in articulation, and that the little bit at the front that's broken off and not quite filling that front blue thing is actually the premaxilla. So it's not part of the maxilla at all. If we do the same thing towards the back, we find that the lacrimal by slice E has taken over completely, and the maxilla is no longer being represented by the specimen, or the specimen is no longer the maxilla at that point. So this gives us a new boundary for the maxilla to examine and compare across the board to other EUDROMAEOSAURIANs, which I might add looks a lot more like typical EUDROMAEOSAURIAN dimensions. So it was a big relief to see this. So I mentioned Echiroraptor before, but I hadn't actually talked about the condition it was in. As you can see from the picture on the left in A, it is quite broken and distorted. So because of this, it's in our best interest to then segment all the broken bits and realign them to get a better sense of its actual morphology. When we do so, we see that the maxilla is much more triangular, and that anterior plate is a lot deeper at its posterior point than it was in the original specimen as measured. So this actually moves it to a less elongate shape and makes up less of the maxillary length as well. The same thing can be said with Deinonychus. Is once we interpret that front portion and the back portion as the premaxilla and lacrimal respectively, we see that the maxilla actually becomes shorter, deeper, and the anterior plate is quite stout in general. It also loses 2 teeth. It was interpreted as having 15 maxillary teeth, but with this reinterpretation, it only has 13. So when we plot this out between Asian and North American forms, the length of the anterior ramus relative to the maxillary length has a lot of overlap. So it doesn't really seem to be showing a good homologous feature that is defining any specific group. However, the elongation, or the length to height ratio of the anterior ramus, does seem to be quite disparate between the Asian and North American forms with little overlap. The one outlier on the Asian form is actually Achilobatar, which is from rocks much older than Velociraptor and its close relatives. And so it doesn't probably fit into that much more restrictive subfamily. The other thing we can look at are characters that aren't describing proportions and instead structures. And these characters might have a lot more weight as long as we can interpret the anatomy of them appropriately. So using the criteria laid out by Samoas et al., I looked at the maxillary characters that were previously described and tested them for their biological independence and for their biological relevancy in terms of codifying specimens. So I chose these two characters as an example. The maxillary fenestra was a very simple character originally, just describing it as either simple or in a distinct fossa, so an extra depression on the maxilla. And the other one was its position within that larger depression or that anterorbital fossa that I mentioned before. So now we can look at the sinus system across these 6 individuals, and we can see right away that, so that's a CT slice of the Velociraptor, and now there's one through Saugon. And what it shows is that their preantral strut, or the bone that divides the 2 chambers of the sinus system, is really poorly developed in both Velociraptor and Saugon. However, in Echiraptor and all the other North American specimens, it is a well-developed strut that is clearly dividing 2 separate chambers. I'd also like to point out in the Velociraptor specimen, the teeth are segmented or they're thresholded in red, and we can see that they actually root much deeper than that palatal shelf. And when the teeth are rooting, especially on such a narrow snout, they're actually limiting the space for the sinus system. It can only occupy the space not taken up by the teeth. So this is important for the next slide to come. But you get a general sense that you have North American and Asian forms separating to some extent. So we look on the external surface, which is more common for us to see. We can now relate those features to this side. So if we take a line matching the tooth depth, we see that the fenestrae are always above the tooth depth. However, in the case of Ornitholestes and Velociraptor, the maxillary fenestra physically cannot be considered low in that anterorbital fossa because the teeth are higher than the low point or the ventral border. Therefore, this character needed revising and removing temporarily until a better one could be constructed to actually capture the biological information. Next, we can look at that fenestra, the big hole, and I've outlined it in orange on Troceraptor and Deinonychus and the 2 Asian forms. And what we see is that in Saugon and Velociraptor, it opens broadly into the fenestra behind it, whereas in all the other ones, it's completely within that anterorbital fossa. The orientation is also different between the Asian forms and being oriented more posteriorly, whereas it's posterodorsally or angled upwards in the North American forms. And lastly, in the late Cretaceous North American forms, just the top 3 here, we see this pneumatic excavation or a deep pit just above the maxillary fenestra, which is unique just to these taxa from the late Cretaceous of North America. So now we actually have 3 distinct groupings. So this helps us to kind of characterize this complex morphology. And I won't describe them all because I did just now, but essentially what happened was that one character got turned into 4 characters, as well as the 12th character was removed and was revised to be something completely different at this point. Now, with all that said and done, all the anatomies out of the way, I'm so sorry, that's always the hardest part. I tried to abbreviate as much as I could. And we've got our phylogeny. So we have our outgroup, the bird line, Avialae, including Archaeopteryx, the sister group to Dromaeosauridae, Troodontidae, and then our Dromaeosaurids in blue. Now within Dromaeosauridae, we have 3 subfamilies that are more basal than the Eudromasaurians, which include the Hulscaraptorinae, Unenlahiinae, and the Microraptorinae, which are the flying dromaeosaurids that you might be familiar with the 4 wings. They're very, very cool. But we'll focus back down here on the EUDROMASORIA. So we have the 3 subfamilies recovered still, Dromaeosaurinae, which includes some of the largest members of the group, such as Utahraptor and Achilobatar. And I've also added Deinonychus to this group, even though it wasn't recovered in this particular tree. There is some support for it within this analysis, but it wasn't a consensus. It was less than 50% support. And so these specimens are found in both North America and Asia, as well as being found from the early Cretaceous, such as Utahraptor, all the way up to the late Cretaceous, such as Dromaeosaurus. Ornitholestinae is recovered as a monophyletic group, and this time it actually includes Echiraptor, and this is based on revising those homologous features to reflect the complex anatomy of the pneumatic system, and that really unites Echiraptor with the Ornitholestines. And then that also gives them a completely North American distribution based on their shared anatomy. This reduces the distribution of Velociraptorinae just to Asia, but we do get a monophyletic Velociraptorinae with features beyond just the snout shape and including those pneumatic structures as well. So just an example of how a homologous character looks. We have the one maxillary fenestra type shown here by Deinonychus, which it shares with Ecolobatar. So this gives us a sense that this group might share a pneumatic structure throughout their evolution, potentially. There still needs to be more discoveries to figure that out for sure. But there's a very strong homologous signal, and we call this synapomorphies when it's uniting a group of that complex maxillary fenestra morphology in Sornitholestines. And then even in Velociraptorians, they also have a unique maxillary fenestra morphology that is not seen in any of the other groups. So it really shows that these pneumatic structures seem to be quite good at following ancestral conditions or following evolutionary trends. So now we can get to the snout dimensions more broadly. We have our phylogeny. We're ready to map these things onto the phylogeny once we examine it. So we're just looking at the maxilla to increase our sample size. And to do this, I employed a method called Pca analysis or principal component analysis. You can do this either with landmarks, so putting essentially dots that correspond to a morphological feature, or you can do it with linear measurements that reflect those morphological features we deem to be taxonomically informative. So yes, there's the details. And then this is what it looks like. You get a nice little plot. You can put little images that give an idea of what is the morphology throughout this square. And what we see is a general trend from left to right, going from elongate to more stout. So I guess if you take the other way, it's more elongate moving to the left. And what's also captured in this is that there's three sort of pillars of groupings, which seem to correspond to the dimensions of the maxillary height to a length measurement. And this also seems to match the trends we see in modern canids of having three distinct snout types. When we look at this another way with cluster analysis, so we take all those dots on the principal component analysis and we see what's closest to each other. We actually get two main groups or groupings, and they do represent the stout forms on the right of the principal component analysis and the elongate forms on the left. Taking that an even step further, we can look at those dimensions, which are the length to height ratios of the maxilla, and we have three groupings that actually match just those dimensions from the PCA. So there's a very strong signal coming in from the dimensions of the maxilla and the snout more broadly. There's also unexpected discoveries while doing this. Because we have this positive impact of an elongation moving to the left, we know things are becoming deeper to the right. And so what actually happens is that specimens pertaining to a single species seem to move towards the right, depending on their size. So what this means is that we might actually have both taxonomy and ontogeny, the growth changes, moving towards the right. And this suggests that in EUDROMAEOSAURIans, at least, as they grew, their maxilla became deeper and didn't grow as fast in terms of length. So they actually became more stout over time. Whereas the PC2, so up and down, seems to capture only taxonomy as far as the features that were there. And I just want to point out Ecolobatar, as you can see, it's encroaching on that deep snout territory, and it's missing a bit of the specimen. So it actually is both in the intermediate and the deep snout region when you estimate its height. So kind of got a bit of both. But anyways, now we can move on and we can show the three maxilla types correlating to their dimensional peaks, as I've mentioned before. And we can use the same schematic that Slater used for his skull types of elongate being a circle, intermediate being a square, and deep being a triangle. So now that we have that, we can map it onto our phylogeny of how these animals fit in. And we see that in Sornitholestinae and Dromaeosauridae, we have a lot of flip-flopping between intermediate and deep snouts, and also the possibility of an elongate snout in EUDROMAEOSAURIA. And this is based on the EUDROMAEOSAURIA project on Facebook, which you can go check out. They have a maxilla that is fairly elongate. However, it's a juvenile. And based on what we know about their trajectories as they grow, it's possible it probably would have shifted into that intermediate form. But that's an aside. What we do see that's interesting is that Velociraptorinae is the only group that seems to be unanimously one snout type, and it is the elongate snout type. So because we can't observe these animals actually choosing what prey they want, we can look instead at the community structure. So then we can make inferences about the prey. So for example, Deinonychus comes from the Cloverleaf Formation, which is a very rich ecosystem, which would have had a community full of small vertebrates all the way through to dinosaurs of massive sizes, such as sauropods and large carnivores. So in a rich ecosystem, we would expect that there's more room for a predator to be more selective or more choosy as to what it wants to eat. Again, we can also see a similar example with Sornitholestes langstoni coming from the Dinosaur Park Formation. Much like the Cloverleaf Formation, this is a fluvially influenced system that is full of vertebrates of all sizes, non-dinosaur, all the way up to the biggest dinosaurs of the time, such as hadrosaurs and tyrannosaurs. And even in the same ecosystem, we see Dromaeosaurus albertensis. And this is a specimen that is fairly confidently known to be a more bitey and stronger, robustly built individual. So it's leaning more to me in towards the large prey specialist or taking on prey of similar size. So to the fact that you have two dromaeosaurs of different snout dimensions in the same ecosystem is indicative that these rich community structures allow for animals to have a wide range in diet. Now, how does this compare to the Velociraptorian situation? Well, so far, all the Velociraptorians that are confidently within Velociraptorinae share the features of a long snout, and they also share a very limited temporal space. So they didn't actually change much in terms of their time of existence. And all of the depositional environments that they seem to come from so far have been semi-arid to arid, only really sustaining one group of large dinosaur, the ankylosaurs, whereas the rest of dinosaurs are at the small size category, maybe encroaching a little on medium. But what's really abundant in these ecosystems are small prey like mammals and lizards. So based on the comparison to Slater et al. Study with the elongate snouts, this would be advantageous for these dromaeosaurs because they would have fast, rapidly closing jaws that they could capture the more abundant small prey such as mammals and lizards. So in summary, we have three different snout morphologies that seem to show strong trends towards these different forms. We have different environments where they come from with different community structures. The intermediate and deep snouts seem to both come from very rich ecosystems from temperate to subtropical environments at the time, whereas we only see the elongate form really popping up in these arid or semi-arid environments where resources were less plentiful. We know that the claw morphology is generally the same amongst most late Cretaceous EUDROMAEOSAURIans, so they're not really doing anything different with their claw at this time. And what this leads to is a hypothesis that obviously needs more testing, but it's an interesting idea that perhaps they follow modern day ecological patterns in which the long snout is beneficial for capturing small prey. And it was more useful because it gave them the guarantee of getting more prey continuously. And the intermediate snout morphology may have been beneficial for a wide ranging diet to gather small and also prey getting closer to their body size, whereas the deeper snouts may have been able to handle prey up to or slightly exceeding their body size and being able to tackle those. Excuse me. The direct evidence of prey is something that's always going to be circumstantial. We only ever capture the moment when animals have died and they're buried, and that's what we have. It's very rare to actually get the moment of the hunt preserved, but we can make some inferences and some speculations until more evidence comes up. And when it comes to Deinonychus, its initial discovery was actually 3 individuals around a large-bodied Tenontosaurus. The maxilla that I described earlier actually comes from the smallest individual. And if we recall that during ontogeny, as they grow, the maxilla becomes deeper, this deep-snouted dromaeosaur that I've reconstructed in the lower left may have become even more deep-snouted as it grew. So this might be an intermediate stage between a small juvenile and an adult. And when we look at the body size of Deinonychus versus Tenontosaurus, it certainly fills into this category of a possible large prey preference, or at least capacity, an ability to take on larger prey, which is similar to the modern gray wolf or examples thereof. Now, it's important to note that this also equally is a possibility, could have been just a predator trap. 3 Deinonychus, separate lifestyles, came in, found a dead Tenontosaurus, and decided to feed on it. We don't know one way or the other particularly, but these are some ideas that, will require more specimens and more testing. Direct evidence of predation in Velociraptor, we have the obvious one, the fighting Velociraptor specimen, where it is locked in combat with a Protoceratops. Now, it is unclear in this situation if this was an attack on the Protoceratops, though some do believe that is the case, undisputedly. But this doesn't necessarily mean one way or another that was their preferred prey. It simply means that while it tried to go for a protoceratops, it was captured in a sandslide or some kind of storm that buried them both. And most predators today are very opportunistic, finding whatever food they can get. So again, we have to take every specimen-based approach to this with a bit of a grain of salt and just look at the taphonomy of the area to kind of get the sense. There is another example of predation in a Velociraptor specimen with a pterosaur bone that was actually in the chest cavity. So pterosaurs, you wouldn't expect too much in the desert, but if it was a difficult place for the pterosaur to be, this could be an example of scavenging. Certainly, a dromaeosaur could only ever attack a pterosaur if it was already on the ground, because I doubt that they're jumping that high. So if we go to Sornitholestes langstonii, we also have evidence of predation. The new specimen of Sornitholestes does show a bone in its chest, which is possibly pterosaur, but it hasn't been fully described yet, so I'm not too sure about that one, but it does show that it did eat an entire element whole. So much like modern birds, like the horrifying pelican, it's possible theropods could swallow quite large objects that you wouldn't expect. There's further evidence of feeding on pterosaurs with Sornitholestes or Sornitholestines. And these are Sornitholestes tooth marks on a pterosaur limb bone. So this is more likely a case of scavenging, as it's just an isolated bone and there's some, not gnawing, but at least some scraping of the teeth while it was eating flesh. So I don't know what it is about pterosaurs. Maybe that was the truth and they're all just pterosaur specialists. So snout shape and diet test. To test this further, now that we have a trend that does match modern day small predators of distinct or 3 distinct regimes of snout shapes, the next steps would be to actually test those structures, to take the 3D models that have been produced, to create a functional model, and then apply the forces of biting and ripping and see if the robust form does in fact manage those stresses better than the intermediate and the elongate forms. This would give more substantial support to this hypothesis and is the logical next step that I would love to indulge in. We'll see what time allows me to do, but yes, sorry. So to compare it to these 3 snout shapes. I never know which button I'm supposed to click at any time. This is all to say that the modern can inform the past. When we think of ecological situations, we sometimes more heavily rely on the phylogeny. And I think that that might be doing a disservice to our interpretations, because in any ecosystem, animals are trying to survive and trying to coexist with other animals. The behaviors and morphologies that come up from those interactions will follow similar patterns as long as there are similar structures. So when we look at this plethora of different snout shapes and faces of dromaeosaurids, it's very clear that they too were undergoing a lot of pressures to change their snout shape depending on their environment. And reanalyzing the specimens with more advanced methods can lead to better interpretations of these possible ecomorphologies or ecological morphologies, such as Deinonychus in fact being more like a Troceraptor or Dromaeosaurus and having a more robust and deep snout than some of its other contemporaries. So in conclusion, ratio-based characters, or things that try to capture dimensional differences, tend to be more homoplastic as they follow the function of an organism. So much like that anterior ramus in its dimensions, it's not a clear homology in the sense that it's clear this ancestral feature something retained. It seems much more able to be changed. As opposed to the pneumatic system, such as the maxillary fenestra with the black arrow, that shows that these structures were a lot more consistent and reflective of evolutionary trajectories or time, slower evolving. EUDROMAEOSAURIAN clades evolved in separate geographic regions, particularly Velociraptorinae and Sornitholestinae, Sornitholestinae being in North America and Velociraptorinae being in Asia. And they also lived in very different environments. The Sornitholestines were in temperate to subtropical environments with a rich dinosaur and vertebrate ecosystem, whereas Velociraptorinae was in a much restrictive and more punishing environment that didn't actually allow for the typical or the broad scoping community structure we see in dinosaur assemblages of North America. And the snout shapes in EUDROMAEOSAURIANs do parallel, at least, modern canids in having a distinct clustering of long elongate forms, intermediate forms, and deep forms. Whether or not these actually pertain to the same behavioral shifts is unknown at this time, but it is compelling and worth further investigation with more evidence that comes up, and probably worth expanding to other ecosystems where maybe large carnivores overlap. That being the weird thing about dinosaur ecosystems is you kind of have to take everything of the modern when you're looking at the large ones and scale it up like to elephant size, and try and imagine that. So with that, thank you for listening. I just thought I would throw out some more creepy googly eyes on more dromaeosaurid skulls. And I would like to thank the following people and institutions for discussion, emotional support, access to data, access to specimens, my funding, and as well the host, the Philip J. Currie Dinosaur Museum. So a lot of people think I'll never thank enough, but thank you all for listening. And with that, if you have any questions, I'd be happy to answer them.
That was very interesting. Thank you, Mark. Yes, we are going to move into the question period. If anyone has any questions, you can just type them in the sidebar. First question, what's next for you after you're finished your PhD?
Hopefully a job. I mean, after I finish my PhD, I'd like to get somewhere where I can be a little bit more stable because of my son and everything. I try to kind of not go too far. But I definitely have a lot of unanswered questions with dromaeosaurs that I would like to come back to after my PhD when I have more time to focus on it again, particularly with the postcrania, so the bones of the skeleton, as well as doing those functional analyses like I talked about. I didn't have time during my master's, unfortunately, to do that, but I would love to get in there and actually get some numbers and some results back for that.
Awesome. I've got a fun question for you. What is your favorite dromaeosaurid dinosaur?
Oh, that is a very fun question, actually. Wow. You know, it's all over the place. It used to be Deinonychus as a kid. I loved Deinonychus through and through. But I think I've shifted to Velociraptor, not because of the movies, the Jurassic Park movies, but because of the specimen I've been describing. So I can't say too much about it right now because there's 3 papers all involving the specimen, but there was one particular Velociraptor specimen that I really loved, and I got to see it in person. It's actually what the skull reconstruction of Velociraptor during my talk was that specimen, and yeah. So I'm gonna say Velociraptor, but it's so hard. I like them all.
Yeah, very hard to choose from for sure. Just going to see if we've got any other questions coming in.
Because I went too anatomy heavy. Never go too anatomy heavy.
I think you just explained it too well and nobody has any questions.
That's what they always tell you to try and reassure you after a talk, for sure.
I'd love to read you some comments here. Got Mermaid Labs that says, thank you, really great analysis.
Thank you.
We've got Jacob saying, very interesting.
I think so too.
And we've got a fan that loves comparative anatomy too.
Oh, good. Oh, thank you. I'm so glad somebody out there was like, yes, anatomy, give me more.
Yeah, of course. Okay, question here from Christian.
Sure.
Could your methods be applied to troodontids?
Absolutely, actually. I think the method should be almost expanded to troodontids as well as kind of overlapping to see where these things are overlapping. Because I think about modern ecosystems a lot. And in terms of the small predators, we have the canids, in here in North America, we have foxes, coyotes, and wolves. But then we also have felids, which are very, very different. So I think troodontids and dromaeosaurids might be a little bit more alike in that they tend to have long snouts, obviously. But what I found was interesting, at least with some preliminary results, is that one specimen of EUDROMAEOSAURIA, the Velociraptor I was looking at, actually has a snout dimension very similar to troodontids, which are more elongate than even the dromaeosaurs. So I don't know what will happen with that, but yeah, I think it should definitely be expanded to them and both within and compared to each other. So.
Awesome. Well, it looks like that's all we have for questions.
Okay.
I'll give it a moment just to see if any more come in.
Sure.
So do you have a dream location you would like to be located?
I mean, it's hard not to like Alberta in terms of paleo stuff. In terms of places I'd like to visit, I really would like to go to Mongolia, even just for a short trip, just because that's where a lot of the stuff I looked at came from, but I didn't actually go to that location. It was mostly housed at the American Museum of Natural History. But if I wasn't going to be in Alberta, I would probably want to be in Ontario area, kind of near the University of Toronto. So
Yeah, you couldn't beat it for sure. Question from Jackson. Did you find much plasticity in specimens of the presumed same species from the same/similar formations?
Yeah, it's a really interesting question, actually. The last chapter of my thesis did actually look at that, particularly with Velociraptor. And it turns out that when you have something of a distinct species, at least where we have multiple specimens, there's a number of features that show very little variation, but there's always going to be some that do show more. And so I guess that was kind of how it was support for this species identification, say Velociraptor mongoliensis versus the new species, is that you have one that seems to show very linear trends. So when you look at different specimens and these measurements, they seem to follow a very linear trajectory with very little variation away from that. And then when you plot this other specimen onto those same trends where they're very tightly correlated, it's just way out there. It's all over the place. So in areas where you don't expect variation and you see it in one specimen, that's when you can kind of say, maybe this isn't a member of that same species, even if it's been referred before, just because general similarity. But at that same token, there were a number of features, if I can try to explain it, on the maxilla, there's sort of that back portion before the antorbital fenestra, so before that hole, that little plate of bone in Velociraptor is quite variable. So its width between the fenestra and the other fenestra is quite variable and doesn't seem to follow a trend. So there is some plasticity in certain features, but then the ones that are taxonomically informative, there's quite a bit less variation. So.
Excellent. Well, that is the end of our question period. Just want to say thank you again for joining us.
Thank you. No, I really appreciate it.
Those of you listening in, join us again Saturday, August 7th at 3 p.m. as Caitlin Schroeder will be presenting the influence of juvenile dinosaurs on community structure and diversity.
Yes.
All right. Thanks to everyone for listening. Thank you, Mark.
Yep. Thank you very much. Bye, everybody.